Okay, so quickly, I want to just talk about sonar for a second. Sonar is based on a lot of the stuff we're talking about in terms of how fast sound travels. Sonar comes from sound navigation and ranging, so there's where the sonar comes from. And sonar uh, wasn't discovered by us; it's been used by a lot of animals for a long time. So bats and dolphins are some of the more common examples, and they use to determine how far away an object is. So they emit sounds about 130 kilohertz range. These waves bounce off objects that they come into contact with, and they come back, and the bat and dolphin, their brains interpret the echo or the reflection of the transmission to determine where objects are. Which, when you see bats flying around, they depend on sonar in order to avoid collisions. So if you think about how fast their brain has to interpret it. Now we've adopted it as well for airplane. Airplanes more radar, but out at sea, they use sonar on ships to detect other ships, or to detect the bottom of the ocean, make sure that there's less chance of striking the bottom. So, going to have a little bit of a investigation or inquiry into that in class, rather than me going on and talking about it for longer than that. The last thing I want to talk about then is the Mach number. So the Mach number is just a ratio; it's a comparison. So we're just going to compare how fast something is moving to 0 degrees Celsius with those conditions. So for example, if we look at my example here, at 0 degrees Celsius, Mach 1 would be 332 meters per second. Mach 2 would be 2 times the speed of sound. So 2 times 332 is 664. Mach 3 is 996, 3 times that. So what you need to do is you need to find that baseline. So the Mach number would change depending on air temperature. So the example we have here, determine the Mach number of a plane flying 850 meters per second in an air temperature of 5 degrees. So what would that mean? It means that we need to calculate the baseline, or what is the speed of sound in air when it's 5 degrees. So 332 plus 0.6 times 5. When you run that through your calculator, oops, you get 3, and you end up with 335 meters per second. So that's what the speed of sound is. So therefore, our Mach number is equal to velocity of object divided by velocity of sound. So 850 divided by 335 gives us Mach 2.5. So therefore, the plane is at Mach 2.5, so 2.5 times the speed of sound. That's all that really means. Right. And final example, I believe. So a plane is traveling at Mach 1.8, or 500 meters per second. What's the temperature of the air? So it's just going backwards, we're just decoding. So we're given Mach number, and we know that it's velocity of object over velocity of sound. So the Mach number is 1.8. We know he's traveling at 500. So we're going to be able to calculate velocity of sound just by rearranging the formula. So 500 divided by 1.8. So we'll find our velocity of sound is 277.8. 277.8 meters per second. Now, second step then is to use your velocity of air formula to determine the value of t. So 277.8 equals 332 plus 0.6 t. As we solve that down, we end up with, let's see here, So we end up with negative 54.2 equals 0.6 T. Divide that by 0.6, and we get negative 90 degrees Celsius. So that's rather frigid. Not sure how realistic, but gives you a feel for the process. So therefore, the air temp is negative 90 degrees Celsius. So hopefully the fuel's not turning into liquid at that point, or freezing solid. So anyway, there you go. That is the end of that particular note. Here's the homework. If you have any questions or problems, please let me know and we'll try to clear those up as soon as we can. Good luck.